Today, we're breaking down the mechanics of QR codes, step by step. By the end of this video, you'll not only understand how they work, but also how to create one. QR codes, short for quick response codes, are a type of two-dimensional barcodes. Unlike traditional barcodes that store data in a single line, QR codes spread their data across a matrix of black and white squares. They come in different versions, ranging from version 1, which measures 21 by 21 squares, all the way up to version 40, a massive 177 by 177 size. These codes can encode all sorts of information, text, URLs, contact details, and even multimedia content. Simply put, the black squares represent 1, and the white squares represent 0. This binary code is what scanners decode to reveal the embedded information. In this video, we'll demonstrate how QR code works by embedding the word Cognizance into a version 1 QR code. We'll start with an empty square matrix of size 21 by 21 and fill it up step by step. Every QR code starts with alignment markers, the large black and white squares found in the three corners, the top left, top right, and bottom left. These markers are essential because they help scanners detect the QR code's position, no matter how it's rotated, sideways, upside down, or even tilted. Alignment markers also serve as a reference for scaling, ensuring the QR code is read at the right size and orientation. For our 21 by 21 grid, the alignment markers occupy an 8 by 8 space in the corners. Next, we add timing patterns. These are alternating rows and columns of black and white squares that run between the alignment markers. Timing patterns are crucial for determining the size of the QR code. They act like rulers, keeping the data aligned perfectly as the scanner reads it. Now, we introduce format information. This step includes two critical elements, error correction levels and masking patterns. Error correction is like a safety net. It ensures that even if part of the QR code gets smudged, scratched, or damaged, the information can still be retrieved. There are 4 levels of error correction. Low, which recovers up to 7% of data. Medium, up to 15%. Quartile, up to 25%. High, which can recover up to 30%. For our example, we'll use the medium level, striking a balance between robustness and data capacity. Let's encode the first 2 bits of formatting information with the pattern for medium-level error correction. Next is the masking pattern. Without masking, large areas of identical colors like this might appear in the QR code, making it harder for scanners to read. A mask applies a formula that flips certain squares to break up these patterns. There are 8 masking patterns in total, numbered from 0 to 7, each applying a unique rule. For simplicity, we'll use mask pattern 0, which flips squares based on whether their row and column indices sum to a multiple of 2. Later, we'll see how this is applied, which will make it more clear. The mask pattern used in QR code is identified by the sequence in these 3 squares. Let's code it with that of mask pattern 0. The remaining formatting bits store error correction data for the formatting information. This single square is unused by the QR code, so its color doesn't matter. Let's color it black. Next step is data encoding. Data encoding consists of 3 steps. Encoding the message, adding error correction codes, and applying the mask. Before we start encoding the data, let's discuss how data is arranged in the QR code. It starts at the bottom right corner and follows a zigzag pattern moving upward. Once it reaches the top of the column, it shifts left and moves downward. This pattern continues, alternating directions, ensuring that the data fills the grid in an efficient and organized way. With this arrangement, the scanner can easily retrieve the data by following the zigzag path. Now, let's encode the data. First part of the message is the data type. The 4 squares at the bottom right corner identifies the type of data encoding. These indicators define whether the code contains byte, numeric, alphanumeric, or even characters from the kanji character set. For our example, we'll use byte encoding. Data type indicators guide the scanner on how to interpret the information. Now we encode the message length. The word Cognizance has 10 characters. In binary, that's represented as 00001010. This length is embedded into the grid using black and white squares. Next, we convert the word Cognizance into binary. Here's how each letter breaks down. Each binary value is then carefully placed into the grid following the zigzag pattern. This is how it looks in black and white pattern. Now we have embedded the word Cognizance into the QR code. At the end, 4 zeros are added to signify end of the message. With the data encoded, we add error correction bits using the Reed-Solomon algorithm. Reed-Solomon is a fascinating and complex process, but we'll keep it simple for this video. These bits act as backup copies, allowing the QR code to recover missing or damaged data. Now it's time to apply the mask. This operation helps break up large clusters of identical colors, like this, ensuring the QR code remains scannable even on reflective surfaces or at odd angles. For this, we use a logical operation called XOR, or the exclusive OR. XOR is a binary operation that compares 2 bits and returns 1 if the bits are different, and 0 if the bits are the same. Here is the equivalent using black and white squares. In the context of masking, we compare each square in the QR code with that of the mask pattern. Usually, different mask patterns are tested and one that gives the best result is chosen. But for simplicity, we are using mask pattern 0 in this example. The mask is applied only to the data and its error correction area, and not to any other part of the QR code. Now, XOR the value of squares in the QR code with that of the mask. If the result is true, the square's color is flipped, black becomes white, and white becomes black. If the result is false, the square remains unchanged. This is how our QR code looks like after the data encoding. The last step is to reserve a quiet zone. It's a margin of empty white space around the QR code, typically 2 to 4 squares wide, which acts as a buffer between the code and its surroundings. Without the quiet zone, the scanner might confuse background elements with parts of the QR code. At this point, our grid is complete, with every square perfectly aligned and all components in place. The word Cognizance is now successfully embedded into the QR code. Now, pause the video and try scanning the code with your phone to see the result. Now that we understand how QR codes are created and how they work, let's take a step back in time to learn about their origin. In 1994, Masahiro Hara and his team at Denso Wave, a Japanese company, invented the QR code. The original purpose was to improve the efficiency of tracking automobile parts during manufacturing. Unlike traditional barcodes, which could store only limited information, QR codes offered a revolutionary solution with their ability to store much larger amounts of data in a compact and scannable format. Although initially used in industrial applications, QR codes gained widespread popularity with the rise of smartphones, making them a versatile tool for businesses, marketing, and everyday life. In summary, QR codes are an incredible mix of simplicity and technology. From alignment markers to error correction, every element plays a vital role in making these codes reliable and universally scannable. Next time you scan a QR code, take a moment to appreciate the ingenuity behind this tiny matrix of squares. Thank you for watching. If you enjoyed this video, don't forget to like, comment, and subscribe for more tech insights.